Thanks for the introduction. Nice to be here. So I'm Tatu Aalto. I'm a lead graphics programmer at Remedy Entertainment. And I'm going to be talking about ray tracing experiments that we've done in Northlight engine. So we are Remedy Entertainment, based in Finland. This is our new office building that we just moved in. You know us from games like Max Payne, Alan Wake, and Quantum Break most recently, and we are currently working on Control and then story mode for Crossfire. In addition to that, we are building our own tech engine and all the tool chains, and we call it Northlight. We have employees from 20 different countries, so wide variety, and we are counting roughly 180 at this moment. But so my agenda for this presentation is to give you a small glimpse on what you can do when you have ray tracing integrated into your game engine. So I'll start by giving you a really quick introduction on DirectX Ray tracing. And after that, I'll walk through a couple examples on what we have tried and how the results were. So we've started off by making reference implementations of for a couple techniques that we are using in the game already. This is of course kind of like experimental, as you can expect, and there is no console support or anything like that, so we can't really make new things that would be only backed up by ray tracing. So this is why the approach is such that we kind of make reference for the faster implementations. And in order to explore, we created a new scene which is not connected to our games. I'll start off with a demo, and we'll discuss some technical aspects after it. I'll recommend to keep an eye how the pieces on this video fit together and how the different aspects of lighting work. So let's check the demo first. Yeah, that's it. Music is made by fantastic Petri Alanko, who's actually going to be talking today, I believe, maybe 4 o'clock. You should check that out also. And yeah, it's actually interesting looking back this demo because this is kind of like the first working version that we had on any of this stuff, and it was made for GDC this year using Titan V, and it was not running real time back then. This is basically a frame capture out of the kind of like fixed frames. So and it has lots of noise and still shooting a lot of samples. The current situation is that this is real time at the moment, and we have added couple basic filters, nothing fancy, but just like basic filtering for this stuff. And it's actually looking a lot better now, but I don't have the capture, so you need to just take my word. So it's looking better, and it's actually running real time easily. But anyway, I'll start with high-level introduction into DirectX Red. Is there people who have used this stuff already? No. Okay. So I'll do a quick dive. I don't go into API details, but to give you some sort of idea of what's going on the API level. So this is DirectX extension from the Microsoft. So it's purely Microsoft's thing. It needs driver support, which there is only for NVIDIA at the moment, but AMD or anyone else can implement this also, and it's actually officially part of Windows RS5 release, which might be out already or is going to be out like next week or so. So the basic API provides you two kind of three hierarchies. So you have top level hierarchy and then you have a bottom level hierarchy. And the idea is that the bottom level hierarchy is kind of comparable for your meshes. So for each mesh in the scene, you need to have a bottom level tree, which is an acceleration structure that the rays are shot on the kind of like a geometry level. Then you have a top level tree, which contains those bottom level trees and builds a scene out of that. So if you check the demo, I've highlighted couple meshes from the demo. So there's, for instance, these 4 chairs, which are the same meshes. So you would create single bottom level tree for a one chair, and then you instance many pieces of that into level. So very similarly than you do with meshes. Then there's a couple other objects, couple bigger sofas, and those you throw into top level tree. The API is built on top of normal DirectX buffers, so the bottom level tree building is really simple. You'll just give your GPU vertex and index buffers, and the API gives you back a bottom level tree. And then when you have a bunch of bottom level trees, you take those, give those and transformations of the objects into API again, and that gives you back a top level tree. And that's pretty much it. You can start shooting rays against that stuff. Dynamic geometry needs a bit more handling. There's no API for doing skinning or any deformation. So there's many ways to do this. For us, the easiest one was to just make a compute shader, which takes in kind of like a non-deformed geometry and just applies skinning on top of that and writes the results in the new buffer. And the idea is that then you have a new buffer and you feed that to bottom level tree builder like you would for static meshes, and that will give you a bottom level tree out. And again, you build the top level tree each frame and just pull these trees together to form a scene. But that's it basically. It's not many API calls. before you can actually start shooting rays. I'll start off by showing a couple of examples you can try immediately after you have done this. So first, ambient occlusion. Ambient occlusion is purely visibility-based algorithm that can be tested by only having the ray tracing scenes, top level and bottom level scenes constructed. Image you see here is taken by shooting 4 samples per pixel using cosine distribution. Maximum length of the ray is set to 4 meters. And hits to geometry are considered black and misses white. And this is basically what you get out. We have added this as a direct replacement for the screenspace ambient occlusion. So we just fill it to same texture and we can compare it to our screenspace solution, which is also pretty good, but it's pretty obvious that screenspace stuff is lacking information. So here on this left side, you can see screenspace and right side raytraced version. So while the screenspace algorithm does pretty good job on grounding things, it's missing information on edges of the screen, and then it doesn't know anything about the surfaces that are not directly visible here. And shooting rays is of course more expensive than just reading screenspace depth. These are numbers for Titan V at the previous GDC, and the situation with the performance is roughly on this ballpark at the moment with Titan V. But translating this to Turing architecture gets you down to somewhere close to millisecond or probably slightly less. So it's roughly 5 times faster to shoot rays on that hardware. So that's already on the more ballpark that you could actually ship something with it. And here is just comparison of different ray counts per pixel. You can maybe see that you have less noise if you shoot more pixels, more rays per pixel, but this is of course really expensive, shooting 16 rays per pixel for the full screen. So you would probably pick something like 2 rays and apply some sort of filtering on top of it. But this is basically your first exercise to try out, and this is already quite interesting actually. Then slightly more advanced, but not too advanced yet. So we implemented path replace sunlight cascaded shadow maps by shooting rays. If you happen to fill shadows of the directional light into full screen buffer before actual lighting, it's very easy to just replace the cascade map lookups with a ray tracing kernel that writes into the same texture. This is basically what we did here. So this is comparison between shadow maps and ray tracing. Again, shadow maps on the left side and ray tracing on the right side. The amount of detail you gain with accurate shadows is pretty remarkable. And of course, in addition to accuracy, it's really easy to do real area shadows with ray tracing. So the clip here is using 8 samples per pixel without any filtering. Sampling pattern is basic blue noise that's changing between frames, and for each sample on pixel, we offset the same blue noise with Sobol sequence and wrap the values on the disk. Here you can see a close-up of the same effect. So as you can expect with ray tracing, the contact points are accurate and you get nice mix of soft and sharp shadows. So while this is nothing radical on algorithm level, it's actually insanely cool to go into game scenes, kind of like your existing game scenes, and see what is the amount of detail that you're actually losing by not having accurate shadows, because it's pretty insane. I mean, the shadow map example I was showing earlier, that's kind of bad, but it's really common situation in games. And even if you would have good shadow map resolution, the amount of detail that you're probably going to be losing is pretty big. And this is maybe even better example. It would be really hard to actually capture that kind of detail with shadow maps. You would need to fit them really well, and actually being able to capture all the spoons and all the kind of like millimeter detail level is really hard with shadow maps with any kind of limited memory budgets. So it kind of immediately when putting this into engine, and it shouldn't take many days actually to implement this stuff. If you have DX12 support, it kind of raises immediately the question that doesn't make any sense to keep increasing the output resolution before you can actually sample all of the detail on lower ones. And again, some performance numbers. Single ray on Titan V is slightly somewhere around 4 milliseconds. On Turing, this would be a millisecond, roughly, or a bit less. But yeah, something slightly more interesting. Those were algorithms that you can implement by only knowing visibility between 2 points. Going beyond visibility requires access to additional data. So in this section, I'll quickly introduce you how we expose geometry materials and lighting to be used in ray tracing kernels. So on geometry hit, the API provides you intersection point in scene and triangle base. Other geometry properties than position, you will need to manually read from some location. This means that you need to have access to all your geometry in a single shader. New DirectX comes with new binding API where you can set different resource bindings for each instance of a bottom level piece in the scene. So let's say I have 2 instances of a chair. Each chair has 5 pieces for different materials, like in the diagram here. I can now define separate resource binding for all these pieces. So in total, I have 10 resource binding records, and each of the record can then have a custom binding for vertex and index buffer, for example. It would be possible to use this same thing for binding materials also, but we happen to already have bindless material system, which allows us to do all the draw calls without binding any data to GPU. So we use that one for these experiments at least. So by packing all the material parameters into single buffer and reserving dedicated space on front of the descriptor heap, we can pack everything so that you can access already with old DX12 everything on a single shader call, single compute shader or single pixel shader, or in ray tracing kernels. And then you need lighting data also. This we already happened to have. We have been doing all the lighting in single shader since Quantum Break, so we already had packed all the projection maps and all the shadow maps into atlases, and all our lighting parameters are in big buffers, which you can see here. This is kind of like a data for one single light, but those are already in big buffers. And that's it. With this information, you can now start doing more complex algorithms, like reflections. So this section is dedicated for implementing reflections with ray tracing. I'll start up with quick comparisons to screenspace technique and continue visualizing how the previous introduced data is used. And as previous techniques shown, we implemented ray trace reflections again as a direct replacement for screenspace shadows, so it's easy to do comparisons. So here you can see a split screen comparison with screen space reflections on the left side and ray traced on the right side again. So this is screen space only. So the reflection ray generation works the exact same way on both screen space and ray tracing techniques. You pick a point on a screen, read the properties of that point from the geometry buffers, just normal geometry buffers that you've been filling with the rasterization, and then based on smoothness, you pick a random direction from the GGX distribution and transform it according to geometry normal. So on screen space, we treat these reflection rays as 2D lines, starting from the screen position and going on screen edge. And in order to figure out if the ray hit any geometry, we take number of samples along this 2D line and check if they are actually, if the depth is such that the hit was done. So it's really easy to miss geometry, either due to not having enough samples, because you can't basically afford sampling all the pixels along that line, or just because the data isn't there. There can be geometry outside of the screen, there can be geometry which is behind the surfaces that are on the screen. And this is just another example. So ray tracing doesn't miss any geometry that's outside of the screen or behind the visible surfaces. On a geometry hit, we need to figure out the radiance transmitted towards reflection ray origin. And for this, we need now the data we packed before. So this is basically the data that the API gives you. So when you get the ray hit, you get the distance from the shooting position, and you get barycentric coordinates on the triangle that the hit was done. So based on barycentric coordinates, you need to read the geometry data and interpolate all the stuff that you need. So, for example, UVs, you need to read from the geometry buffer. So these are UVs at the hit location of the reflection ray. So this you would need read from the geometry buffer. And then with materials and UVs, you can get diffuse albedo. And this is lighting at the reflection location. And finally, combining this with material and Fresnel will end up looking like this. This is reflection-only visualization. So in order to get the final image, you combine this with diffuse and specular lighting, direct diffuse and specular lighting, and you will get this one. We didn't have, as I said, we didn't have a lot of time back at the GDC to look into noise filtering, but I have a couple image loops to visualize what kind of problems you will end up with this kind of framework. So this is the raw image you will get. This is actually from a slightly different lighting setup to make it more clear. In here I have a direct single sunlight shining into the scene, into the location, and you can see that because of rays kind of hit on the different locations around the geometry, you start to get flickering, and this is really hard to filter out from your picture after it's done. But with ray tracing, it's actually easy to do some tricks. So with ray tracing, the most standard way to get the variance of the image noise down is to shoot more samples. But shooting more samples for the whole picture is of course not feasible, because that's insanely expensive. But with the ray tracing API, it's really easy to pick some locations and shoot more samples for only single pixels. So on this picture, we've taken pixels that are 3 times brighter than the widest point on the scene, on the picture. and on the average picture, and we shoot 3 more rays on those bright pixels. So this already gets the noise down by a lot. And you can always combine it with small damping. This is basically not very nice way to do it, but it's very commonly used, even on production, kind of like film quality rendering. Then couple optimization points. These are now stuff that was not on GDC demo. So while it would be perfectly possible to use ray tracing to solve shadows and at reflected surfaces, we use shadow maps for most of the lights in the demo. The only exception is the sunlight. Since we use cascaded shadow maps, we only have valid shadow data for the screen. So for that one special case, we actually need to shoot rays to resolve shadowing situation. But using shadow maps is a lot faster, and it's not very easy to spot the difference, kind of like shadow accuracy problems on the reflections. Because if you still have sharp shadows on the kind of like the direct lighting, that already gives you kind of good impression of resolution. Probably the biggest and easiest win you can get at the moment is to split ray casting and shading into separate passes. Introducing heavy shading load into ray tracing kernel seems to cause some scaling problems, at least with current drivers. So in order to avoid wasting resources, it's good to only export needed collision information from the ray traversal and leave the actual shading onto just normal traditional compute shader. This is super simple modification of code, and it cut roughly half of the execution time on our case. And once you've split your shading work out from the ray tracing kernel, you will learn that shading is actually the bottleneck. So since the rays for reflections, for instance, they hit all over the world. So that's really bad for caches. So when you start reading data for all those locations, you will get lots of cache trashing, and that will basically kill the performance. While we have been seeing numbers, kind of like a shooting rays is around single millisecond, like one millisecond on new hardware, and shading can actually, just like doing simple shading at the hit location, can easily cost 7 milliseconds or so. So that's the ballpark where you start from. So we've done some small tests on this stuff. I don't have anything super fancy to show you. We tried out a simple per material grouping, and even with these kind of small tricks, you can cut half or third of the load easily. So this is what we are doing at the moment. This is not super elegant, but it works decently now, pretty okay. So yeah, this fits into couple hundred lines of code. So the idea is that you first calculate amount of hits per material in ray tracing kernel, then you allocate range per material and to store the hits into, and write actual values in order into these slots. And then finally you run shading in this sorted order. So you basically run shading per material, not per kind of like ordered by material, not ordered by pixels. And then the final optimization that we've been using now is to limit the traverse distance of the specular rays. This is kind of a bit engine specific. So since we store indirect illumination into volume, we can read low detail radiance anywhere in the scene. So we are using this to optimize and reduce variance of lighting on rough surfaces. So the rougher the surface, the shorter the rays are that we are shooting. And this works actually quite nicely because it cuts performance from shooting the rays, and it makes shading more local, and then it also provides you better data which has less variance, so it's easier to filter out. Of course, it's not ground truth anymore, so there's that. And this is again some performance numbers on Titan V. So the ray shooting is a lot faster on new hardware. Shading is pretty much the same, or at least on the ballpark. And in here, in this picture, I have diffuse global illumination interpolated from the volume texture. So yeah, sorry. This is all I have from reflection. So let's move to diffuse, indirect diffuse illumination. So in this picture, I have diffuse global illumination interpolated from volume texture. The approach you see here was implemented for Quantum Break, and it's in use by default on our engine. So the voxel resolution of the GI data here is 25 centimeters, and we combine the results with screenspace ambient occlusion. I showed you earlier that we have a path to replace screenspace ambient occlusion with ray tracing. So let's have a look how that looks. So this is the same data combined with ray-traced ambient occlusion. So the result is better, but this still looks like ambient occlusion applied on top of volume data that doesn't have enough resolution for the case seen here. So instead of just shooting a lot of rays around to resolve global indirect diffuse lighting, I'll talk a bit about improving sampling of volumetric global illumination and resolving indirect near-field diffuse lighting. So I'll break this down with few diagrams. So our pre-computed volume global illumination is stored in sparse volume texture. This is kind of like a 2D slice of that volume. So the grid on the screen represents the data, and each crossing contains indirect lighting data that has been calculated with path tracer. The blue shape on top of the global illumination volume is static geometry that we use for calculating the data. You can see that the dense parts of the GI volume are on the areas that overlap with the geometry. So in addition to static geometry, we have, of course, in scene, there's dynamic geometry. The smaller green piece is dynamic, and dynamic geometry is not used in pre-calculation. So part of it resides on low resolution area of the volume. So there's a couple problems in using lighting directly sampled from the volume. First, we'll miss the dynamic geometry completely. It just isn't there. And we've been relying on screenspace ambient occlusion to ground dynamic geometry to the rest of the scene, which is pretty much the standard solution for this stuff. And the second problem is linear filtering of the volume data. So on the surfaces that are not aligned to volume, we get staircasing that can be quite visible due to low resolution of the volume. So it's 25 centimeters, so the blocks will be fairly huge. I have some examples later. And finally, the low resolution will cause lighting to leak through thin geometry. It's possible to try weighting sampling so that it will leak a bit less, and this is what we use in Quantum Break. We kind of take normals and try to bend data slightly, but ultimately you're just moving the artifacts because you don't actually know the underlying geometry and you don't know the structure of geometry compared to your GI volumes. So instead of sampling the volume directly on the surface, we can shoot rays with ray tracing and sample global illumination on the locations that didn't hit the geometry. So positions that are not on the surface are less likely to contain leaked lighting in our data. So this will reduce leaking and result in smoother interpolation. So the simplest thing to do when hitting the geometry is to consider sample black. This is pretty close to calculating ambient occlusion with the benefit that it helps with light leaking and results in better interpolation. So let's look at the comparison between this and then direct sampling of the volume data with ambient occlusion. So this is the GI volume sampled directly and combined with raytraced ambient occlusion. So if you look at the table or a magazine on the bottom left corner of the image, you can clearly see that there's something wrong going on. By modifying the way we use the volumetric GI data, we can fix many issues that can be seen when using direct sampling. I'll toggle a couple times back and forth. So this is direct sampling and raytraced AO. And this is the fixed one. So what's happening here is that since the GI data that we have is bound to have resolution for 25 centimeters only, there's going to be darker values below the table, and there's going to be brighter values on top of the table. And if you just take a sample from middle, you will get basically something random. And that's exactly what's happening with the magazine. We are basically reading global illumination values that are below the table. And now if we modify that so that we don't read the values at the location of the geometry, but we shoot samples away from the geometry and read the GI there, we will basically get incoming radiance from that direction, and that will have a lot less artifacts. It's of course possible, because it's volume data, it's of course possible that you end up shooting close to some other geometry, which will then cause leaking from other direction, but it's a lot less problematic than actually having this kind of direct occlusion problems. And this is the case of staircasing. The case is pretty much the same as on the previous. We have in the demo we have this large dome, which is brightly lit from down, and from the behind of the surface there's lots of darkness. So what happens on this kind of curved surface is that you will start to get this kind of staircasing on the volume. And this is again can be fixed by using the same method. So just getting the sampling out from the surface helps a lot. So on previous examples, we considered rays that hit the geometry to be black, and that fixes already a lot of problems. But instead of darkening the image, we can of course do better and evaluate lighting and material, like we did with reflections. So this is the same stuff I showed you earlier, which considers samples that actually go and hit the geometry black. So this is kind of like a ambient occlusion type of effect that you get in combination with global illumination. But you can of course also go and sample lighting, and then you will actually get global, kind of like near field global illumination. The accuracy on the first bounce is something that you could not easily store in the limited volume size. So with this kind of method, you can actually get global illumination data down to accuracy down to something like millimeter level again, instead of 25 centimeters. That is our normal default. So this is the direct lighting information that was used for near field. And this is direct lighting combined with indirect diffuse. And this is final lighting with specular also applied on top of. And this is the final image. And again, performance numbers. So you can probably see a trend of rays costing around 2 to 5 milliseconds for full screen, for full HD picture on Titan V, and on Turing that's down to roughly on ballpark of 5, so it's around millisecond or less. And the shading is of course really depending on what kind of shading you're actually doing. So you can do something really light, or if you throw something more complex there, then that's going to be expensive. And that's all. So in summary, DirectX ray tracing, it's providing you super easy access to state-of-art GPU ray tracing. GPU ray tracing is of course nothing new. It has been there, and there has been libraries to do this for quite a while already. But having this all in DirectX 12 makes it super easy to actually integrate into existing pipelines and do hybrid methods combined with normal game rendering. So that's super interesting. And it's super interesting even if you are not planning to ship anything with it. I would definitely recommend at least going into level of implementing shadows, because that gives you very good idea of what kind of detail you're missing from the scene. And yeah, performance is obviously getting there with new hardware. And it's possible to combine this stuff with the existing methods that you already have. So there's not much to lose, really. And this is shout out to all the guys who have been making the scene and the tech also. And mandatory hiring slide. We have lots of open positions, Remedy Games/careers. Also graphics programmer roles if you're interested of this kind of stuff. And that's it. Any questions?
So could you give us a bit more details about the scene, and did you actually try to run those techniques on maybe like some bigger, on real game scenes, maybe like bigger areas with dynamic characters and stuff like that? Thank you.
Yeah, this is actually fairly representative of amount of stuff that we would have in game. This actually probably has more geometry than our normal game levels do, because this isn't really optimized for shipping. So this is kind of extreme case. But yes, we have integrated all of this into Northlight, and Northlight is used by all our game projects. So yes, it is possible to check also Control, for instance, with ray tracing, and we have already announced in Gamescom that we are going to be shipping Control with ray tracing support. So it's obviously only on PC, not on consoles. We will only implement things that we can also match on consoles, and consoles will still look great, but on PC you can. This is basically kind of like a quality option thing. You can toggle on ray-traced reflections if you want on PC. So yes, we have been running kind of like complete games with this stuff, and it works fine.
Okay, hello. Thank you for the great talk. I got a question about the irradiance voxel space. I was solving similar problem, and I got problem when voxels, or the points where the irradiance is measured, is inside the geometry. And I wonder, how did you solve this problem?
Yeah, that's problematic. I mean, since it's volumetric data and it's not on surface, it will have points that is inside the geometry. We've been kind of going back and forth a bit on this stuff. In Quantum Break, when baking the data, we kind of like identified the locations that are inside geometry. So this is basically done by just counting how many rays did actually hit backface geometry and how many actually hit kind of like valid geometry locations. So with that classification, you can get some kind of rough idea on if you're inside that stuff or if you're outside of the stuff. And then the basic method, what you will do is you'll just throw out the rays that hit back faces. That will of course cause problems because then you need to somehow invalidate the volume data, and that's going to be either black, or then you will delete somehow valid data onto areas that are kind of like considered invalid. We are doing, at the moment, we are actually not accepting any invalid data in our GI volume because it's less bad looking having something filled from the neighborhood onto the sample locations that are inside the geometry. But yeah, it's a hard problem, and actually detecting if you're inside the geometry, that's hard because you can have overlapping geometry and so on. I guess triangle winding would be kind of like the most robust automatic solution. But we are actually, at the moment, we are detecting kind of like interior and exterior spaces by just doing a simple voxel dilation. So we voxelize everything, and then we pick some location. We kind of like artists are dropping points into scenes that they consider to be kind of like outside of the geometry, and then you just fluid fill your voxel space, and that will give you kind of like interior space of the stuff.
Hi. So has ray tracing informed you on how we should shape data for ray tracing? So I believe right now you're using the same data for geometry-based rendering and ray tracing, but is there like taking advantage of crazy ideas like vectorial-based definitions or things like that?
Yes, I haven't really gone there, no, to be honest. Of course, when combining this stuff with rasterization, you want the data to match somehow. So you probably shouldn't go too far. For instance, yeah, using LODs on ray tracing would be problematic because then your geometry doesn't match anymore, and then kind of like if you start shooting rays from the rasterization results to some other geometry, you will hit back faces and all. You will basically get all the problems you get with shadow maps by using different representations on those. So yeah, while it would be possible, I'm not sure if it's feasible. Maybe.
And just a follow-up question: is there extra memory consideration? So you've talked a lot about performance, but do you need to allocate more buffers, or is it lighter on memory?
Yes, there is. Bottom level trees do take some amount of memory. It should be a lot less than the original geometry, of course, because this is basically tree data, and it's compressed heavily. But to be honest, I don't actually know exact memory footprint of this, but I've seen memory consumption actually being fairly high, but I believe that's mostly from kind of like intermediate representations that the drivers use to actually do the bottom level trees. The bottom level trees themselves are fairly compact. But yes, you can. It's fairly memory bloaty at the moment. But I guess the guys are actually trying to fix it. So there's ways to make it better. But in theory, the acceleration structures for the ray tracing, of course, should not take as much as your geometry.
How slow is it to actually create those bottom level trees if you've got a lot of animated data going on? Is that expensive? Can you tolerate creating tens or hundreds of bottom level trees for many animated characters? You said you need to recreate them each frame after you've animated the data. Is it CPU, GPU?
The acceleration, ray tracing acceleration is running on GPU. So you feed GPU buffers and it's running on GPU. It's running completely on drivers, so it's a black box. You just throw stuff in there and it returns you something. It's fairly fast. There's a couple options. You can rebuild kind of like there's a fast path for building which produces slightly worse trees, I believe. And then there's update path, so you can kind of like give the existing tree and just update that, and that will also give you slightly less optimal ray tracing structure, but it's faster to build. The build times are, this is really hand wavy, but our build times for bottom level trees with a lot of skinned characters are somewhere on millisecond, maybe 2 if you have a lot of them, but then you will have a lot of characters. I think tree building has not been a lot slower than actually running the skinning at the moment for us, but we haven't really optimized this thing a lot yet. So these are probably really vague numbers.
Fair enough, thanks.
Yeah.
How do you handle plants and vegetation because those have opacity in the textures?
Actually, we don't have foliage in this yet because, yeah, alpha testing is easy. The API provides you a shader, basically shader stage, which is called AnyHit or something like that, maybe AnyHit shader, and that's called always when the ray tracing traversal finds a geometry point, and at that shader you can just return true or false if you actually want to use that connect point. So you can kind of like implement alpha testing with that stuff. You just read the texture alpha values and say that, okay, this wasn't hit. That of course doesn't give you transparency, kind of like real alpha, that's on-off toggle. We've done, or the NVIDIA engineer actually, that's been working with us on this stuff, has done some experiments on implementing transparent rendering with this stuff also, kind of like shooting direct rays, so the transparent surfaces that are directly visible there, like glasses and so on, and it works pretty well. Then it's kind of like shooting only transparent geometry is fast because you usually don't have that much transparent geometry, and you can filter out all the opaque surfaces from those passes, so you can just shoot against transparent glasses, for instance, and you probably don't have that many classes in your levels, so it's fairly fast. But yeah, there's other problems then. You need to somehow blend it with other stuff, like with particles and so on. So yeah, it's not a solved problem.